Greetings to all. Today I'll be talking about my seminar topic, which is exploring asymmetric key algorithms, security and its applications. So we'll just move on to the topic. So why I took up this topic is because in the present world we are talking about security considerations. We're talking about your asymmetric algorithms which are being used in the real life applications. And we're basically focusing in this seminar about the communications and the transactions, the data exchanges which are made using this asymmetric keys. So why I took up this topic is because you know uh, presently there's an emerging technology known as quantum computing, and as you guys might know that quantum computing is set to break systems. It does not just break the system, it breaks the standards of the system. And as we tell as standards, it's mostly the encryptions. So we have been using some traditional keys, basically your RSA keys, Diffie-Hellman. But today I won't be talking about Diffie-Hellman, but I'll be talking about the key exchange which involves Diffie-Hellman. And so that's the part of it. Mainly, I'll be focusing on the traditional keys, uh, which is your RSA, and the not so old but still used in the modern computing, the ECC cryptography, basically your elliptic curve cryptography, which is said to be much stronger and faster in minimal requirement resources, and which is being used by modern computing. So we'll be talking about the post cryptography, post quantum cryptography, and all the solutions to it. Okay. So yeah, as I told you, we'll be talking mainly about the online transaction, the the document exchange, and all the communications. So let's start with the RC. Ravist, Shamir, and Adelman. These were the three guys who started making this cryptography. The math behind is primary number factorization. So they take two numbers and they factorize, and further they do certain calculations based on encryption and decryption using mod function. And here, when we talk about RSA, just to go back in time, this was developed in 1977. So these three scientists basically built, and cryptographers, you can tell. And the key length of 2048 is said to be the most secure one, like not most secure one, but the most adaptable and the secure one. And these have vulnerabilities. The future predicted one is a quantum attack, and as being of 2048 bits, uh, factoring algorithms like the GNFS and the SNFS is said to be very uh, potent vulnerability to the RSA. But presently, as we are using 2048 bits, which is uh, present computing powers, neither a supercomputer can't process it in maybe a million years. So let's just get to the history behind that.
In 1977 led three scientists, Revest, Shamir, and Adelman, to come up with an encryption breakthrough. Today it's known by their initials, RSA, and it works something like this. Every person has two really big prime numbers, all their own, which they keep secret. They multiply these numbers together to get an even bigger number, which they make public for everyone to see. Now, if I want to send someone a private message, I use their big public number to garble my message, and I garble it in such a way that it is impossible to ungarble without knowing the two prime factors that made that number. This is an asymmetric key system, since different keys are used to encrypt and decrypt the message. So it's easy for my intended recipient to decode, but impossible for everyone else unless they can factor that large public number. Now, someone could try to factor it using a supercomputer and the best-known factoring algorithm, the general number field sieve, but modern cryptography uses prime numbers that are around 313 digits long. Factoring a product of two primes this big, even with a supercomputer, would take around 16 million years.
So, but not for the quantum computing. That's what we have to go know, and we'll go deep into that later on. So here is a diagram of how your RSA works. So for the keys, we'll take 5 and 14. Okay, they'll be so the message, let it be 2, which is hello. And when you take the keys, you take the mod of the key 1, and then the power of the message to the first key. Now you encrypt it. Now this encrypted one, basically they actually have, the private keys. So you need private keys. Public keys are used to encrypt, and private keys are used to decrypt in the RSA cryptography. So here you take the keys, and this key, the private key, is only known to the recipient and the sender. But the public key is being made visible to avoid attacks and to showcase that this is the key which are being used. But this keys can't help you decrypt the message. It can only encrypt the message. So here again, to the encrypted the cipher hash, you take the power of the first key. Like it's your primary numbers basically. You take two primary numbers, the prime numbers, and then you just use it as the keys, and then mod of the next primary number. Further, when you calculate it, it gives you 2. So this actually is based on a formula which is d approximation of e to the power minus 1 mod of e. So we'll be thinking why we use asymmetric keys, or maybe most of you know where all we use the asymmetric keys. So you must have heard about the SSL certificates. Their fingerprints are being generated through asymmetric keys. The Bitcoin's transactions happen through asymmetric keys. That is, we'll be discussing further on how the transaction works in the your decentralized systems. And SSH, as you know, the secure shell, also uses the asymmetric keys. You can generate both like RSA for your own system, so that somebody else can connect. If you have a private key, and if somebody figures out your private key, they can connect to your system using those private keys, which are generated in the .ssh folder of the Windows. And PGP actually is a signature key, which is used in mostly Linux kernels use this PGP. It's a little complex to understand, but yeah, it's generally used there, the PGP keys. So we'll just go a little depth into the math behind the RSA. So here you take two prime numbers, P and Q. Take an example, then you compute this number into a n value. It'll form a bigger number. Now you take a Toissian function. This is what denotes the Toissian function, and is equal to P minus 1 into Q minus 1. When you calculate, you get 288, and then choose an encryption component. Your encryption component will be set to be your public key. That's what you'll be using for encryption. Now, you will calculate the modular multiplicative inverse of E modulo of Toissian function. Then the public key will be your 5, as I told you, it will be your 5, and then the n value. Okay, and the same way, your private key will be 173 after you do the modular multiplicative inverse of E modulo Toissian then. So that's where I told you, you take the modulo of like D is equal to E inverse of modulo of Toissian function. That's what you do, and that's how you get the private key and the public key. And further, let the cipher of your message be 123. To encrypt, you use C, that is cipher is equal to m to the power E and mod of n. So you'll be getting this value, and when you decrypt it, you'll be using like the cipher over that is 29 what you received, and then m will be basically your message cipher. So your c to the power d and mod n will be 29 to the power 173, which is basically your private key, one of your private keys, and yeah, that's your private key, and then mod of 323, actually 123. So further we move on to the next big, cryptographic currency, I mean cryptographic key, elliptic curve cryptography, where a mathematical function or a mathematical term, which is elliptic curves, are being used, and they are defined over finite fields, because when you draw a graph, x and y can go to infinite, but here we'll be declaring a imaginary line which will cut short the thing to a finite field, making it a max value. And the efficiency is, if you compare the keys, like if you take RSA and RSA versus ECCS, the 2048 keys generated in the RSA will be 348 bits of key in the ECC. That's how efficient ECC is. They're mostly used in compact systems, as you don't need much resources to encrypt and decrypt the key. So the resistance is high compared to RSA, but most of the modest computing systems use ECC rather than RSA. But if you're running on a lower systems, they say ECC is better than RSA, but not all systems have integrated this ECC into their environment. So, as I told you, suitability for constrained environment, all compact systems, and this basically depends on the function or the curve equation you generate for the encryption. And quantum computers, obviously, they can beat up all the traditional, they can break all the traditional standards and cryptography. So take a curve, okay? Let the curve be, uh, you know, let the curve be y square is equal to x cube plus ax plus b. And when you draw the curve, maybe this you'll see the red line, right? And that is the curve. And you take a point on the curve. Now you draw a tangent which is across the x-axis. It makes a point. Now draw it onto the reflected onto the x-axis. Again, then draw a tangent, and then again reflect it. then again a tangent, and again a reflection. So that is how a key is formed. So imagine as I move my mouse, there's an imaginary line which will be defined as max value. And as the tangent goes, it diverges. It diverges away. It's not converging, it's diverging away. So imagine if the max value is kind of here. Imagine the amount of tangents and reflection points it can form on this curve in the graph. That is huge. So the number of times what can be formed is like uncountable. That's where the efficiency of this cryptography comes into play. So here you can see how your ECC is, it's a random number generation, RNG. So here it generates a they use different cryptographies. Like you can see, for encryption they're using AES, and then for the hash they're doing the hashing over here, where they generate ECC key of public and private. So the private has been using the created share secret is basically on a public medium. You send the key, which is not secure, but both the people share it along over a public connection or a public tunnel. Basically, your Diffie-Hellman key exchange, and then you hash it, and then further you use your HMAC and then add it to the MAC of the system, and that's how you get your output. So here, if we think about it, the mathematical property of an elliptic curve over a finite field is being used. Here, what happens is a scalar value. See, when you make a tangent like this, it forms a vector, right, on a two plane. And when you tell a curve, the curve is a 2D. It's not a 3D. It's only the ECC only uses 2D, and that may be one of the drawbacks, as a curve can only be performed on a 2D. I mean, there are ways you can perform it on 3D, but I don't think it'll matter in terms of this. So here you take the public point, which is the base point will be P. So base point is this, the G which is shown, and then you use those and calculate the public point. But here, as I told you, the number of reflections and the tangents form are numerous. So just knowing the base point can't help you with it, because the max value has to be known, and even if you know the max value, the number of reflections is unknown. That's where ECC holds its strength. So ECC does not directly but it is used in the key exchange and digital signatures. So ECC it does not provide encryption, that's true, but as keys you use it. For example, for the Intel One API, you must be using this for the local host connection to the cloud, or the Intel Cloud Dev Cloud. As now, let's move on to the post quantum cryptography. So right now, as it's a generation of quantum computing coming up, and IBM is, as we hope, not far away from discovering those qubits which are presently missing in the system. And after that, the whole traditional cryptography is gonna break down, because they are set to break. As always, there are always breakers, and these breakers, if they get into the quantum computing realm, they're gonna break all the traditional cryptography and the systems which run the traditional cryptography. So to restrain from that happening, we are, you know, we have to adapt to the post quantum cryptography. So you might know the NIST, National Institute of Standards and Technology. They had asked for the help, you know, with cryptographers all over the world to send papers related to quantum computing cryptography as a defense against the emerging systems. So all over the world, they have sent many papers, but a lot of them got rejected as they were set. They were quoted. I can't tell the word, but yeah, they were quoted basic, as in they don't crack the system. They don't touch the standard which the NIST needed. But four of them are selected, and they were all based on latest. So you might be wondering what is the latest. So a latest is just the number of vectors which can be, you know, uh, driven from a point of start and moved across the imaginary points. Okay, so that's known as a lattice. So we'll be mostly focusing on lattice because lattice is presently the most adaptable one, and the rest of it is actually, they're just overlay on the lattice based. So this, why I am talking about PQC is because of the quantum resistance. And here I'll be just showing you how the classical algorithm is different from PQ algorithms. So here you will be using, your classical methods, your certificates, CA, all those things to just sign the documents and stuff. But here you'll be using a composite certificate. So composite in the sense it's vast. It's a combination which is used to sign digitally, and this will encrypt the document or a transaction in such a way that your quantum computers can't break it. So the math behind is basically a lattices, and they have a resistance towards the classical, what do you say, attacks and the quantum attacks. The classical attacks, like just last we discussed, the special numerical, uh, you know, the GNSP and SNSP. Um, so the math behind it, we basically create the public and the private key, and even the decryption happens the same way. So I'll be just telling you how. So this is the latest, and how we form n number of vectors will matter, as we if we move from the point v1 to v2, just add the v1 plus v2, will give you 2v. So just like that, you just keep going, and you'll get the. So see, as the vector's magnitude and the direction is this way, if you traverse from this point to this point, it will become v1 plus v2, because v1, and then you need this vector to traverse to this point. So just like that, you will form lattices. Okay, and this is one way of how they encrypt the keys. They take a modulo of 4 for every of this numbers. For 4, the private key is 4 random numbers, and modulo of 4 for every of them. And then encrypt the 0 bit with all of it, and encrypt the 1 bit for all of it. Okay, so I'll be just showing you how this is generated. So take a vector from a point 0, R1 and R2. Take two vectors of different directions and different magnitudes. So if they keep moving further, they form a a pattern around this, and the number of ways it can traverse to different points is known as lattices. Now take a point C and just think about how you can traverse from here using the standards of this both vectors. You have to traverse to this point. So you found an easy method. So this part is said to be the public your private key, and this is said to be your public. So that was your private key, and this two vectors is said to be your public key. So this is showcased by the sender, that this is how they have encrypted the key, but this is not the way. And here is the actual message. So when you try to traverse from here, it's a long way, and there are many ways which can be used to traverse to this point. And we must even think that when we encrypt, there's a noise which has been set, included by the sender to further encrypt this point or the message which is C. Now, if we consider this in a 3D dimension, just imagine the number of possibilities it can move to take this directions and the magnitude to traverse to C. So that's going to be a huge value, because just imagine a plane uh, and a circle. So R is your radius. If you take it as an area, it becomes R2. And now if you take it to a 3D dimension, it becomes R3. The latest points which will be mentioned over the points over here are the dimensions basically. So just as you saw, it was a 3D dimension. Right now we are including dimensions of 100, and then the newest systems will be implementing your 1,000 dimensions. So imagine the latest points which can be figured out over there. It's gonna be millions and trillions of it. So these are the ones which break the quantum attacks. They resist the quantum attacks. This is how your private key works. So if you have the sender's private key, that's how easy it will be to just see this is a sender and this is a recipient. Now, if the recipient has the private key of the sender, this is going to be the source. So this is the public key, okay? And if you have a point, so sender has kept a point 7, and now he makes a sound around the point, and that is said to be the message, okay? Now over here, this is said to be the public key. If somebody who tries to crack in, if they try to enter the system, just imagine the number of routes they'll have to take right way to enter to the system. It'll be infinite, and it won't be the right way. But when you have the private key, it's that easy. You just traverse from here. So they're just comparing and showing you how a private key and a public key matters, and especially in the latest. So now we'll be comparing about the strengths. So RSA relies on the challenge of factoring large semi-prime numbers, and ECC is built on the elliptic curve. And here, a post-quantum algorithm uses problems that resist quantum attacks. Okay, so classical versus quantum. So as you know, RSA is threatened by the quantum computers using Shor's algorithm. I guess you all know Shor's algorithm, the most common algorithm which is used for SHA encryption. That is a risk for the RSA itself. Now ECC has a resistance towards quantum attacks due to its difficulty of solving, as it uses the elliptic curve discrete logarithm problem. And here the impacts of the quantum computing are being raised on RSA. and ECC retains its security strength against quantum adversaries, making it promising choice. Because as you know, the ECC, when the max point is set to a higher way, and they also give shorter keys compared to the RSA, like shorter bits of key. It's much convenient and it's much secure compared to RSA. So here, as we talked about latest based security, we have, uh, I mean, scientists and the cryptographers have found this to be the most apt one during the post-quantum times to be used. And they have a longevity as these follow up to the most robust solutions to be during the quantum periods. And here, even though I have introduced you guys to the traditional cryptographic keys and also the post-quantum keys, it is our choice that what is adaptable by the system and how applicable it is for us and how reliable a key can be for us to be used. So that's totally our decision to make. Now we'll be addressing about the vulnerabilities. So mainly there are two vulnerabilities which will be taken. One is the implementation flaws. Most of them, as you are not, as they're not educated towards the implementation or the working of a key, you tend to use it in the wrong ways. Maybe you take an RSA key of a shorter, maybe 256 bits of RSA key, and you try to use it for your systems. So the main backdrop will be that the general number field seals will be a target for such encryptions made by the RSA, as they can crack down the numbers using those factorization methods. Basically, what your general number field sleeves are when RSA keys are factorized. That's when they found the number field sleeve, NFS basically. So during the factorization was the time they found this part of the thing. And when they found the GNFS, it is basically that you take a number of, 100 digits after take a number which contains 100 digits. Okay. Now that has to be factorized. What do? You find the most suitable special numbers which are related to this number, which can, be a prime factor of the number. And then what you do is you basically like make an equation, you know, like a plan to solve a jigsaw puzzle. You make an equation, and this equation further has to be defined in a space, a field, they say in the mathematical field. That is, a space where this equation is relevant. So if it is not defined in such a place, then of course you can't make sense of maths when it is not applied in the right place. So after you apply, further you find these, they break down slowly. When you solve this equation like a jigsaw puzzle, you solve it and it'll break down. What you have to further do is all the solved puzzles, you have to keep them as a blocks. They form blocks, and further you can just crack down the whole thing using the GNFS. There is one more which is special number field sleep. You'll not be focusing on that. It basically works on the same methodology. So here there's one more vulnerability which you're talking about is the side channel attacks. So here, I guess you'll be knowing about how there are hardware attacks which have been done. For example, you take your own computer. Uh, when you use secure boot in the BIOS, what it basically does is it'll load up the defense kernels first before it loads up the other files and all the OSs and stuff. As you know, the modern systems, they have the TPM, which is basically our security chip developed by Intel. They secure your systems from all the password attacks, all the chip attacks, all those kinds of attacks. And further, if you're a Windows Pro user, uh, there is a KDA, basically a kernel defense authorization that can be activated. But as I am a home user, I don't have those features. So these, they do it at the right time. See, they just attack using the analysis of power consumption, time information, or even sound. See, when you tell a system is secured and active, there must be a time which the system, goes down. Like, even though there is basic security, it cannot stand up all the time. There's some time, there's some place, there's some time which your walls fall down. That's when they conduct this attack. These are the side channel attacks. And they find out the security information after they get in using these methods. So next we'll be talking about other secure communications, which are main application of these keys. So you must be knowing the TLC, TLS. So they are basically in the transport layer, and you'll be using your secure socket layer to tamper the eavesdropping and all those other methods which are used to tamper data. And then you'll be just like WhatsApp, Telegram, such are secure messaging apps. So even there, your the recipients or public key can be only decrypted by the sender's private key, or vice versa. And email encryption, as you must have seen, when you receive mails in your Gmail, if you further look for the digital signature, it'll be like mail by, signed by. You'll see those authors which are signed them. For example, when Google has signed them, and if the mail is secure, they'll write gmail.com, Google, and stuff like that. So further, we'll move into the digital signatures. Here, we'll learn about the creation. So you know how they form hashes. They use a hash function, and then they encrypt the document, and they make a digital signature which does not and which cannot be tampered further by any system. Now, this key, if it is sent to the recipient, and if the sender has to send the document and send the document signed, the signed document and the recipient's key can be compared to find that it is the authentic document that the recipient had to receive. So this is used in e-commerce and even document authenticity, as I told you, like for example, um, take, I had downloaded this, an update. So here there's a 7-zip app. Here you can generate the SHA 256 bit of this file. Okay, so this you see is the key of the file. It's a digital signature basically. And now when I downloaded, along with that, I downloaded the SHA which was given in the website. As you can see, okay, I'll just tell you that this is the key which came along with it. Okay, so it's basically a SHA key. So I'll just open it and see the key. So this is the key. So this was provided by the author in the website while downloading it. Okay, I just downloaded it because I always check the security of it. Now, if you go to the part, I have just taken both the keys, as a string, and then further I've compared it. Okay, I pasted both of them, simple thing, and then I compared it. So here you can see that yes, both of them match. Now you can say that this was made by the Inkscape's author and not some random file, or it wasn't from a phishing site that I downloaded this uh, file, which could have been malicious. But now, as I verified, I can be sure that it's not malicious. So let's move on to the next part. Here we learn about key exchanges. So key exchanges basically are, there's a direct transmission over an unsecure line, okay, or an insecure line where you share the secret key. So the protocol involves a modular exponentiation and exploits the difficulty of computing discrete logarithmic algorithms. The shared key is subsequently used for symmetric encryption. Okay, Diffie-Hellman is symmetric kind of encryption, but this when it is sent, they are sent in partial ways. Okay, and they are exchanged intermediately, and then they are further shared. So this increases the security where VPNs and the secure chat applications use them. Now let's move on to the IoT security. And in IoT security, we have to always remember that ECC is the most convenient one to be used in the IoT devices, as they are much compact and they provide a constrained environment to work on. The processing and uh, uh, the processing is limited basically, and the resources too are limited. So here is where the efficiency of the ECC comes, which takes advantage of the limited computing power, and even your transmissions happen over ECC, which can reduce or nullify the tampering happening during the data transmission over sensors. Now even you can authenticate services and networks using this ECC keys. They even have to work with few other keys when you use it along with the network, as you might have seen uh, here. They work with a lot other keys too, and then they form a strong pack. So here the MAC addresses are being encrypted. Okay. Uh, okay. So even the firmware, when you download, basically, imagine you downloaded the firmware into this laptop BIOS, a new update of the BIOS, and when you check for the uh, you know the PGP key and the signed key of the, what do you say, the firmware, it has to match. If it is not matching, it means that the data or the firmware is being tampered, and that shouldn't be installed into the system, which can cause many other problems. Even can give a root access to the wrong person. So as I told you, let's move on to the blockchains and cryptocurrencies. The asymmetric keys in the blockchain are, possessing the asymmetric keys. The public key is used for the address, and the private key is used for the transaction. So as you know, uh, when you receive transactions, the address, uses the public key. But when you sign a transaction, when you sign a person's transaction over the blockchain, as it is decentralized, that's how you verify your transaction by signing it. You use a private key. So this also uses asymmetric keys in the blockchain. And when you make a transaction, the sender signs the transaction with the private key. Okay, and the recipient can verify the transaction's authenticity using the sender's public key. So the sender's public key is visible to everyone, and that's how they authenticate the transaction, as I told you. Uh, so coming to the conclusion of what I have to talk about the thing is that, in simple words, RSA is original code. ECC is a faster and a safer version. But there's something which has to be done during the post-quantum times, and that is your latest based keys. And this will restrain you and resist you against quantum attacks, which will be happening in the future. and these can lead to wars. So you always need to know the working of a key and even try to implement and learn further aspects of a key, so which can, prevent so many cyber wars which are being predicted to be happening in the future. Mostly, if they say if there is a third world war now, it's going to be a cyber war. So thank you.